Hello, calculus fans! So we've talked about computing triple integrals in cylindrical coordinates, but we do have another coordinate system that we could use, and that's spherical coordinates. So we're now going to talk about computing triple integrals in spherical coordinates. Remember that in spherical coordinates, we label a point P, rho theta phi, where rho is the distance from the point P to the origin. Theta is the usual polar coordinate of the projection of P into the xy plane. And finally, phi is the polar angle. That's the angle that OP makes with the z-axis. Here's the picture. So you see rho is this distance from P to the origin. Theta is the polar coordinates theta of the projection of P into the xy plane. And then here's the polar angle phi. Remember, we have some conversion formulas. X equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. In spherical coordinates, we have an analog of a rectangular box, and that is the spherical wedge. A spherical wedge is the set of all points rho theta phi, where rho goes between A and B, theta goes between alpha and beta, and phi goes between C and D. We're going to go ahead and assume that A is bigger than or equal to 0, so we're not going to ever talk about negative distances. And we'll say that beta minus alpha has to be less than or equal to 2 pi. That way we're not looping around and around. Let's show a picture of a spherical wedge. This is a spherical wedge. All right, this picture is a little bit busy, but really what's going on here is that the bounds on all three coordinates are constants. Remember that when we defined a triple integral, we did so by dividing our region of integration into little rectangular boxes. Now we can show that dividing a solid into small spherical wedges always gives the same result, that you'll still be able to evaluate an integral. So what we do is we divide our region into smaller spherical wedge, E sub ijk, by using equally spaced spheres, half planes, and half cones. So we chop this up into little spherical wedges. Now what our picture shows is that EIJK is approximately a rectangular box. Now it has dimensions delta rho. The other dimension is rho sub I delta phi, because we have an arc of a circle with radius rho sub I and angle delta phi. And our other dimension is rho sub I sine phi sub k, and that's because we have an arc of a circle with radius rho sub I sine phi sub k and angle delta theta. These three things are approximately the dimensions of this rectangular box. So if we multiply them all together, then we're going to get the volume of this spherical wedge. So that means we can say that the volume of E sub ijk is approximately equal to delta rho times rho sub I delta phi times rho sub I sine phi sub k delta theta. Multiply all these together, and what we get is rho sub I squared sine phi sub k delta rho delta theta delta phi. That means we're now able to write down an approximation for a Riemann sum for the triple integral. And we're going to get the sum, this triple sum, of f. And notice that we have now replaced x, y, and z with the appropriate spherical coordinates transformation. And because the volume of the box is given by this expression, we have to put that in at the end. What we should notice is that this last expression, this triple sum, is a triple Riemann sum for this function, f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi, times rho squared sine phi. That means if we take a limit of the triple Riemann sum, we're going to get a formula, and this is the formula for triple integration in spherical coordinates. So we'll just give the formula now, and then later on we'll use this. We can now say that the triple integral over e of f of x, y, z dv is equal to the integral from c to d of the integral from alpha to beta of the integral from a to b of f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi, times rho squared sine phi d rho d theta d phi. And E is a spherical wedge. It acts like a rectangle in spherical coordinates. So E is the set of all points rho theta phi, where rho goes between A and B, theta goes between alpha and beta, phi goes between C and D. I want to point out, of course, that we have a rho squared sine phi in here. This is what's called the scale change factor. It's just like the R that we used in polar coordinates or cylindrical coordinates. From now on, when converting from rectangular coordinates to spherical coordinates, we just have to put in this rho squared sine phi. Okay, that's all for now.